system that would be the best translation system in the world 3 years ago in a day on commodity hardware, which is pretty remarkable. And I think question answering is moving there now as well. For some of these limited domains, we have systems that do as well as humans. They're still not at the point where we're doing really, really complex multi-hop reasoning, but for simple things like just finding the answer when it's very clear, and starting to get to the point where they can do a little bit of reasoning on top. They're also, question answering is a super active field. Stanford alone has, I think, at least 3 or 4 question answering data sets. It's a little bit much. We'll be talking about Squad, which is a data set of passages from Wikipedia. So it might be, for example, the Wikipedia page about George Washington, and the question might be, where was George Washington born? But there are all sorts of ones to test different aspects. Stanford also has one for conversational, like if you were interacting with a computer and you were asking it questions, and so more of an interactive QA setting. And one data set that I really like that I think shows we still have a long way to go is narrative QA. And so a lot of these data sets have sort of biases where the way they're made is you have a paragraph of text and you give it to a Turker and you ask them to ask questions about it, which has a lot of biases in sort of how it's generated. One neat thing narrative QA did is they have a book, they have people write summaries of the book, and then people write questions based off of the summary. So you can't, it's not just going to be super local, like this paragraph contains the answer. It'll actually require potentially looking across a long arc. Today we're not going to focus on those aspects, but just sort of the lower level building blocks and what it takes to do well at these sort of simple Squad-like question answering tasks. So to make Squad a little bit more concrete, again, we'll have a passage of text, in this case, a passage about teaching, and then a question about it. And the important point is this is extractive, it's not abstractive. So abstractive would be maybe the exact text isn't in here, but I'm expecting you to write free-form text. Extractive means at some point there's going to be from token 4 to token 7 is the answer. And so this system isn't doing the language model. Like in translation, for example, if you're doing this like a seek-to-seek problem, you would read in the passage, read in the question, then generate the answer token by token. This system is trained to just predict what position, where is the start and where is the end. And the scoring is done, there are 2 metrics, exact match and F1. Exact match is just, is this the same thing? After like lower casing, removing punctuation, etc., does it contain the same content? And then F1 is a combination of precision and recall, and it's a little bit more forgiving. So in this case, here's an example where it has too few words, and here where it has too many words. In both cases, the exact match is 0, but it does still score pretty high in the F1 metric. Let's see. So a high-level roadmap for the talk. Oh, let's see. So I wanted to start out by just talking about high-level models for text, so RNNs, convolutional architectures, language models, seek-to-seek models. Spend some time talking about attention, the transformer architecture that comes out of that. And then talk about how you use these to build a QA system. I'm just going to talk about the building blocks of QANet, so talk about the structure, the individual components, so Squad is actually not a very large data set. It's 100,000 question answer pairs, but a lot of the passages are duplicated. They have many questions about them. And so you have to really use external knowledge. Like you can't, if you just train a system without like any pre-trained word vectors or pre-trained transformer of any kind, you do pretty abysmal on it. I don't have the exact number offhand, but it's not anywhere close to competitive. And then one additional trick for handling these sort of small data sets is you can augment your data. So one trick to do this is, for example, you might take your passage of text and replace words with synonyms. Or one thing that we do is we take a passage of text and we use a translation system to go to another language and come back. And the hope is it maintains the semantics, all the information, but may say it slightly differently. We'll talk through some of the examples of that. So just to start off, who has trained a language model before? Yeah. Who's like familiar with RNNs and such? Okay. Everyone's sort of familiar with like bag of words type models or like word vectors as a concept. So I'm just going to walk through these at a very high level, make sure everyone's roughly on the same page, and then talk about attention and some of these architectures. So one of these classic tasks is just one of the classic data sets is IMDb sentiment analysis, where it's like, okay, I have a review. Are they saying the movie's good or is the movie bad? So for something like this, it's pretty obvious, right? There's no negation, there's no sort of complex reasoning. But to build a model on this, you don't really need anything more complicated than a bag of words. And what that's going to look like in deep learning land is you have each of these tokens, you map it to a vector. The simplest way of embedding it is just going to be a one-hot vector, like this is this token, this is not that token. And then you do some sum, average, some sort of reduction over them, and you train a logistic regression. On a lot of tasks, this is actually going to be pretty hard to beat. Surprisingly strong baseline. But again, this doesn't take into account any word order. It doesn't know that awful came after was, etc. It also doesn't take into account, like if not came before awful, it wouldn't know. It doesn't have any sense of ordering. You can make it a little bit more complicated by adding sort of n-grams to it. And, oh, well, OK, before we get that, actually, you're roughly familiar with the idea of these word vectors. So the simplest one would just be, I have a fixed vocab. I say, this is vocab item 5, this is vocab item 4, and you bed that into a vector. You've probably seen these sort of word vector analogies. One really, really cool aspect of, so more or less you can learn unsupervised word representations from text. Very roughly you say, given this word, what are the words around me going to be? And given the words around me, what is this word going to be? And so you can learn some co-occurrences, and it'll probably learn, oh, this word is very positive, this word is very negative. And so what this is illustrating here is in these vector spaces, you seem to have some sort of neat geometric properties, where if you take the vector, if you take queen and the vector representing queen and the vector representing king and subtract them, then you get the vector that separates man from woman. And this seems to hold up for a lot of different sort of relations. Like you end up so these are always somewhat approximate visualizations, but you end up finding that the relation between countries and capitals sort of have their own subvector space here. And there are lots of techniques for training these. The kind of classic are there's word to vec, and I don't know how to make that. This guy go away. I don't know, OK. Well, oh yeah, so this one is the given the words around me, predict my word. So predict myself given my context. And then there's SIPgram, which is given my vector, predict the average of the vectors of everyone around me. And so these are from the early 2000s. They work incredibly well, or surprisingly well. And you basically have to start with a system like this to get decent results on these question answering tasks. So now we have high-level view of word vectors. You can learn them. You could just do like a simple one-hot embedding. And now we can go above bag of words, and we can start to add sort of n-grams. So convolutions here, this is just you're applying the same weights at each of these positions, and it's essentially just learned n-grams. So you could do n-grams manually, like you could look in your corpus, count how often does awful follow was, and that would be its own sort of item in the vocab. But here it's actually constructing the n-grams and learning them online. But again, it doesn't actually know that this came after this. It might be able to roughly figure it out from the fact that they both saw this word in the middle, but there's no explicit position information. So now moving on to RNNs, you kind of can introduce that explicit position information by processing it sequentially. So RNNs, you just have some function that's going to take my current input vector, my previous hidden state, and return a new hidden state. And so in this case, this is an example of the simplest RNN. And in the case where we're doing sentiment analysis or one of these simple classification tasks, we'll just, so previously we would just take the sum of the vectors and then do classification off of that. In this case, we take the final hidden state and treat that as the output. Again, this is like mapping a sequence to a single label. In this case, this has some downsides in terms of you can't process it in parallel. You have to process it left to right. But it does have explicit sequential information, and LSTMs, RNNs, et cetera, have been massively successful. Like I think NMT systems, most of the translation systems still use them. They're slowly being displaced for many applications by convolutional and transformer architectures because you can train those faster. But they're a surprisingly hard baseline to beat. And so one application where these are commonly used is language models. And you can frame a lot of problems in terms of language modeling. Just as an example of what that is, if I ask you all to say, like, OK, the quick brown fox jumped over the lazy blank, you can probably fill in the blank. Anyone have any ideas? Well done. Yeah. Their language models are slightly off. So you can fill in the blank. And this is a classification problem. You're saying, given the words I've seen so far, classify the next word out of all possible vocabulary I have. What is the next class? And so when the first language models, they were just fully feed forward. So this is from early 2000s, and this would be saying, okay, I want to predict, the desired output is dog. I have the quick brown fox, et cetera, et cetera, et cetera. You just have the index. You grab their word vector from some embedding matrix, and then they just flatten them, concatenate them, apply a bunch of feed-forward layers. And so there's no, you're only doing a single word at a time. There's no recurrence. This is like you're applying, you have a window, you're sliding over your sequence, you apply your feed-forward layer. You apply your feed-forward model, and you predict the next word. When you're doing this with an RNN, you actually kind of pack them all into one. So this is, in fact, in this case, this is 5 little classification problems in one. In this case, you're trying with absolutely no context except start token, predict that the first word is the. And you get more and more and more context. And again, at each point, you're predicting the next word. And this turns out to be an incredibly powerful, I'll talk a little bit later about this is incredibly powerful for learning representations. But you can also phrase a lot of problems this way. So if I have a language model like this, it's trivial to turn it into a translation system. You've now changed it from, OK, just predict the next word to, OK, I feed you English. I give you the German token. Now I want you to do language modeling, but I expect you to produce German. And so this was actually the first seek-to-seek systems. They just took a language model. They ignore the English side when applying the loss, and they apply the language modeling loss only on the sort of target language side. And so this works decently, but one aspect of this is when you're decoding, there's causality. I can't say bitte until I know that the previous word was ja. Whereas, so in this case, I have to go forward. Whereas in the encoder side, I can actually encode both directions. I can apply convolutions. There's no sort of causality. And so this is how you get from this to sort of these. So this is encoder decoder, but we're just passing the hidden, we use the same RNN, we pass the hidden state across. Sort of the more traditional encoder decoder you've probably seen is we're doing English German. We have the English come in. Let's say we apply a bidirectional RNN here. We apply a bidirectional LSTM or CombNet transformer. And so we have some encoding of our source text. And on the decoder side, this is where we have causality. It's a language model. It's going to generate, conditioned on our context, generate the desired language token by token. And so the question then is, OK, how do I get this information over to here? Before attention, the way to do that would have been, OK, let's say I have a 128 hidden unit cell here and 228 unit cells there. I take those hidden states, project them down, and use it to initialize the hidden state of my RNN, and then it just spools it out. So I give it its initial states, and it's just going to generate the rest of the sentence without ever looking at the input again. You could do something fancier where you condition it, but that's a high-level idea. And so where attention comes in is, it's how do you connect this input to the decoder? So you've probably seen attention, hopefully looked at the Attention's All You Need paper. It's a bit hard to understand. I have yet to find a good explanation of attention, I'm sorry. But this sort of gives you attention. I think it's sort of easy to anthropomorphize it. But so here are 2 examples. This is doing English-French translation, and this is an image capturing system. Image capturing systems look exactly the same as the one we were looking at before, but the encoder, instead of being an RNN, is an inception or ResNet of some kind. So right now we were talking about the seek-to-seek problems. If I have an image to seek, just the encoder changes to be an image encoder. And so what you're visualizing here is, OK, so it sees this image, it runs it through a ResNet, it gets the feature map, and it's going to generate, you want to generate a caption token by token. And what we're visualizing here is, when it's generating this token, where was it looking in the image? And how it does this is, in your feature map, you're basically going to assign a weight to it based on my current state. So as I'm generating, I have my current hidden state here. And I take that vector and I use it to assign a weight to each position in my image. And I normalize it so it sums to 1. And that's what this is visualizing. So when it was about to output frisbee, it was looking at the part of the image that had the frisbee, likewise with dog and stop sign. And you can see a similar effect with language. Let me see if this is. So also, I highly recommend this post by Distill. If you get a chance, they have some very, very nice interactive illustrations of RNNs and sort of fancier attention mechanisms. Let's see, what do we got? OK. Sorry, 1 second. OK, here we go. So this is saying, OK, So we had English come in, and we're generating French one by one. And you can roughly see sort of, so this attention originally came out of an attempt to align between source and target. So we want to know what was it trying to look at when it generated the word sign. And so here, for example, you can see, so it makes a lot of sense that it has a lot of weight on the exact synonym. Okay, you can't actually see it on this projector. You'll have to trust me. There is another faint line over to agreement. And so you can, I hesitate to like assign, I think it's very easy to read into these sort of attention maps. They're hard to interpret. But it kind of like intuitively kind of makes sense that, okay, if I see the word signed and also an agreement, that kind of increases the weight that I'm going to produce the verb signed in whatever my target language is. But so this was originally out of an attempt to just sort of explain the translation systems. But it also became just the most effective way in practice of actually creating them. Oh, right, actually we have another example over here. Also, attention is tricky to understand. Please don't hesitate to ask questions. Slow me down if I'm talking too fast. Just yell at questions at any time. Okay, so attention is a weighted sum of vectors. So you have some, in this case, I have some memory here. Each of these vectors just represents what is the two-dimensional vector that lives inside this cell. And let's just say that this is sort of selecting what is our query vector. So in this case, I'm taking, this is my query vector. This is the memory I'm attending over. And there are basically two steps. One is assign a weight to each one of these. And the weight is going to be a function of the dot product between my query vector and that cell. So just some distance metric. And then you normalize that so it's a probability distribution. So when you just take the similarities, it doesn't necessarily sum to 1. You apply a softmax so it sums to 1. And then you weight each of these vectors by their weight and do a sum. So in this case, for example, this vector has the highest similarity with itself. So a lot of it passes through. It has some similarity with this. So this gets a little bit of weight. These don't get so much weight, but they do have a little bit of an effect. So this output vector is heavily weighted toward these two. So let's see. So yeah, again, attention is a weighted average. In all these illustrations, I'm just treating as if the memory and query were the same. In reality, you have some input. You do a separate projection to get the sort of the queries and the memory. But at a high level, just imagine you have a single vector for each word. To get the output of my word at the next step, I do a weighted sum of all of the other word representations. The weight is determined by how similar is my representation to their representation. And so this is in contrast to a convolution, where you're going to apply the same, A, there's a fixed receptive field. B, you're going to apply the same kernel at every step. So I kind of think of attention as a dynamic convolution. It's sort of tricky in these cases because it has a full receptive field, but you can actually limit its receptive field for efficiency. And then it's like a convolution where the kernel depends on the content of what you're convolving. So this is the vanilla form of attention. In Transformer, they use something called multi-head attention, which is essentially you do these in parallel. So before doing attention from the word licked to every other word, I'm going to project each of these vectors to two separate vector spaces, and then do attention inside each of them, and then recombine. And so you can think of this as maybe different heads will pick up on different things. I think if you look at a translation system, for example, one head might pick up on preposition binding, like what does he refer to? And another head might pick up on handling parentheses or closing clauses properly. Again, hard to interpret, but they do often seem to do things that make sense. So now we have this tool of attention, and that sort of gives us how we go from this encoder to decoder side. So the input, again, let's just say we're doing an RNN here. The input X is going to be a function of A, the embedding of the input token, and B, a weighted sum of the encoder side. And it's going to do this at every time step. And so when it's looking here, it might put a different weight on different parts. So maybe here you'd hope that when it's about to produce ya, it's putting a lot of weight here. Whereas when it's about to produce beta, it puts a lot of weight here.
The initial state of the decoder is always the same?
So most people set it to 0. You can make it learnable. More parameters seem to always help, but it really makes a negligible difference. Yeah.
But like for every question, the initial state is like, and this is going to be begin.
Right. Yeah. So in this case, let's just say it's a 0. If we have an RNN 128 hidden units, length 128 0 vector, you could also make it learnable, or you could make it a like linear projection of a reduced sum over the encoder.
Okay.
So but in practice, it doesn't matter. I've found that if you remove the state, like passing the state explicitly from encoder to decoder and just use attention, it's fine.
Okay.
Yeah, attention's pretty high bandwidth in general. Yeah, because also like if we were, let's say we used a linear, like we do a sum and then we use the final hidden state to pass over, you're still, like if you just did a sum of the hidden states or something, the attention's kind of doing that every step, right? It's getting to decide, but it's just getting to decide how to weight them and how to sum them up. Okay, yeah. And so any other questions? Yeah.
Yeah, could you go back to your slide? So you kind of drew an analogy between attention and convolution, right?
Yes.
So I have a pretty good understanding of convolution in the sense that the receptive field is fixed, but also you kind of parameterize how you want to weigh your neighbors, and then parameterization is being learned in how you want to weigh your different neighbors in this receptive field. How does attention compare to that, and where do you parameterize it, and what part is learned and what part is not?
Okay, so what are the learnable parameters inside attention? And let's see, so the connection I make to, have you seen hypernetworks per chance? So that just is, when I'm applying a convolution, the weights of that convolution are somehow a function of my data as well. So one option is we have a learnable variable, it sits over here, we pull off the shelf and we apply it. Another option is I have a kernel 3 conv, and those weights could themselves be the output of a neural network. So I kind of think of attention as something like that, where this is sort of a convolution where the weight is a function of the data involved. It's not an exact mapping, but I think it's a powerful way to think about it. It's more of a sort of dynamic routing thing.
But there are no actual learned weights in the attention.
Okay, so in simple attention, simple attention is I have a memory and I have a query vector, do the dot product, get all the weights, and then do a weighted sum. In like transformer, for example, there's, I don't think I have a good illustration. There's 3 parts. So I have my input come in, and I have 3 1-by-1 convolutions, essentially. So I have a linear layer I apply to get the query space, the vector space, the query space, the key space, the memory space. And when you're doing the weighted sum, you'd say like, okay, take this vector. I've done 3 projections: query, key, value. When I'm trying to decide what is the output here, I take this query vector, I dot product with the key value of all of these. I take that weight, I multiply it by the memory or the value projection, and sum that. And so you can actually get away with, for example, you could not have a value projection, and you could make your key and query projections very, very small. Like you could do these similarity lookups in like 5 dimensions, and that's fine. In fact, I get the sense that way more heads with very small dimension is better than few heads with big dimension. I don't yet have empirical proof for that, but I'm pretty sure. So you have, let's see. So attention, I think, is more about information routing than shoving parameters into it. So the next, I'm just gonna skip ahead a few. So this is the full transformer architecture, which you all saw. The high level, I'm gonna ignore the decoder for now. So we have inputs come in, we do word vector lookups. In their case, I think one point I haven't pointed out yet, attention is a bag of words model. It does not know that this comes after this. And so you actually, one thing you could, for example, have a small RNN or some chain model that runs across this and it can kind of count internally. Or you can do learned, you can just have a learned embedding for like, this is the embedding for position 1, this is embedding for position 2. One kind of crazy thing that, let me see if I have Oh, there we go. Yeah, so there's I think y'all probably saw this. So one thing that Noam, the author of this, does is instead of doing positional embeddings, so you have your word embeddings, and you add a bunch of sines and cosines at different frequencies, and it turns out the model is good enough to like back out the position information from that, and it can figure out the relative position. Kind of remarkable that works, but it seems to in practice. Let's see. Right, so input comes in, embed the tokens into word vectors, add positional encoding, in this case the sine cosine, but you can do learned ones. And then all of this is inside a ResNet block, so there are identity connections all the way through. You do multi-head attention, but most of the compute and parameters actually live up here in the feed forward. So I think one general sense I have about a lot of these architectures, so in non-data limited regimes, like we're doing language modeling or translation where we have function and limited data, all that really matters is your total parameter count. It doesn't really matter where the parameters live. If we made these attention layers tiny and just put all of the parameters in feed forward, then that would probably work pretty well. So in the sort of standard transformer, let's say we had 128 dimension, we would do all the attention heads in 128, and then we would project up to like 1,000 or 8 or larger inside the feed forward and apply nonlinearities and such and project back down. So I kind of think of attention as it does all the information routing from place to place, but all of the like compute is in these feed forward layers. And when I say feed forward, it's a 1-by-1 convolution. You have a sequence, apply a convolution with kernel 1 over it. Does that sort of answer your question about where parameters live and how to parameterize it?
Great. Could you clarify again what you mean by key value?
Right. So I think one of the readings had a decent illustration of this. Let me see.
Isn't the illustrated transformer one?
I think this guy might have also had a decent one. 1 second. Oh,
No, that was it.
that was it. It's hard
Go
from.
for it, yeah.
Oh, all right. There we go. I feel like he had a more. Here we go. Okay. So, right, we have these words come in, we embed them into vectors, and then in this case, like so, each of these is going to be length 3. We do a projection from this length 4 vector to a length 9 vector, and we split into 3 parts. And so now we have query, key, value. When I'm computing the score, it's going to be a function of this query and this key, this query and this key. So I now have a weight on each of them. I'm going to multiply this weight by the value. But so 0.88 times v1, 0.12 times v2, sum them up to get our final one.
What's the, I guess, the logic behind deciding to use 3 projections for each encoder state rather than 2 or 1 or something? It
probably honestly works if you don't have any. So I think it makes a lot of sense for queries and keys because you can do multi-head. So because you're doing these similarity lookups in different vector spaces, and so you kind of want it to be able to care about different things in each of those. I have not tried. I suspect if you didn't do the projection on the values, it would still be fine. Or you could probably
just do a dot product between the two.
Yeah, I think it's
symmetric dot product.
I think it's like it was the simplest thing that worked, or I think it was maybe the first thing that worked. I don't know.
It makes sense to say like, oh, okay, if we want to say, go from here to here, like from one word to another word, we want that to be different from, the other direction. So that's, I guess, where this query and key idea came from.
So in this case, actually, let's see. Oh no, you're right. Yeah. So if one word, so it's not a symmetric relation. That's true. I don't actually have a strong sense for whether the value projection is. Maybe all you have to do is just project the queries or just project the keys. Like I think there are a lot of surprising properties of transformers that we don't know yet.
Yeah.
Like even without recurrence, can you learn simple synthetic languages like grammars? Like we actually don't know. There was this paper recently called Universal Transformer, so the same way an RNN does weight sharing lengthwise, it's doing a transformer with weight sharing depthwise. So it's like it would be like you had a ResNet where you use the same weights inside every ResNet block. And that actually you can compute more powerful, theoretically you can compute more powerful functions because you can do for loops essentially. But we don't. I think there's a lot of cool stuff to explore with this. I don't know, maybe you could probably just try removing. So I think the important point would be, though, if you did in fact remove the values projection, to put the parameters somewhere else. Like, I suspect if you remove the values projection and put the equivalent amount of parameters into the feed forward layer, you get the same results.
Okay, that makes sense.
Let's see. Any other questions on these guys?
From the embedding to the query value.
So it's just so in this case, it would be a 4x9 weight matrix, do a linear projection, and then split it into 3 parts. And the one important thing about transformer is, so we're talking about these like very, this for like a single head example, but in practice it's extremely efficient because all of these weird like summing and computing the query key compatibility is just a bunch of packed matrix multiplies. So it's extremely fast in practice. Let's see, what do we got? So yeah, so we're talking about, so you can do encoder decoder with this. You can also just do a normal language model, but in this case, when you're generating, so this is where the self-attention thing comes in. When I'm generating this token, I get to look at all of the preceding memory. It may be possible that for practical reasons, you need to like not look all the way back if you have very long sequences. But this is nice because it's much easier to copy long sequences. It seems in practice it's hard to get RNNs to remember things for more than a few hundred steps. And this has less of that problem because there's sort of an O of 1 connection from here to here versus an RNN would have to traverse the whole way. Cool. And I think with that, I'm going to talk, any questions about attention or what we've talked about so far? Move on. Cool. So we're going to now talk about a high-level view of what does an architecture look like for QA, some of the details of the QANet architecture, and then at the end talk about this transfer learning approaches. So this is a pretty generic architecture. Really, basically when you tell me you have a problem that is map 2 sequences to a sequence, there's really like 4 things you can do. In this case, it's even easier because we don't even have to produce a sequence. We just are predicting what is the start and end position. And so this is like, if you say, give me an image to sequence problem, it's like, great, I'm going to have an image encoder and then a sequence decoder. In this case, we have 2 sequences in and technically a sequence out. But what we're doing here is we take our paragraph of text, we take our question, we embed them, let's say using word vectors or some sort of pre-trained embedding, apply roughly transformer to get, so we now have an encoding of each of these separately. And there's a step which Adams will talk about where you attend from each position in the document to each position in the question. So you can now imagine if I'm at a word in the document, let's see. So if you have, for example, a page about George Washington, the question is, when was George Washington born? You'd like for every year in that document to sort of be aware of the question in some way. So this is sort of letting information from the question propagate to everywhere in the context. And so now we've kind of fused all the information, and off of here, it's just apply a few more layers and predict what position is the start position, what position is the end position. And Adams is going to walk through this in a bit more detail. Yeah, there we go. Right after I hand him the mic.
All right, thanks David for introducing the basic concepts and techniques for NLP. So now I'm going to introduce a very general framework for QA system. This is an example which is called BiDAF. It is short for Bidirectional Attention Flow. So the BiDAF architecture contains the following layer. The first layer, which is at the very bottom, is the embedding layer. So first of all, for each token of the context and query, it put it into the embedding. So it contains the word embedding and character embedding. And the word embedding is the pre-chain fixed vector, which is called globe. The character embedding is a chainable one. And then we concat those 2 representations. Then each token is now being a vector. Okay? And then we pass this vector to an encoded layer, which usually they use, here for example, they use LSTM or other RNN. The idea of this layer is to make the representation context aware. Okay, so then we pass those context aware representation to the attention layer. The attention layer, the idea of the attention layer is to compute the interaction between the document and the query so that the representation become query aware. Okay, here they first compute the query to the context and then the context to the query so that they can do a fully fusion of this information. And then those query aware representation is passed to another encoder, another or more encoder layers, and which is again LSTM or INN. And finally, on top of this encoder, we do a classification problem and then predict the starting and end point. Okay, so this is the basic idea of this BiDAF structure. We can see that the RNN or LSTM play a very important role in this system, and actually is the building block of the encoder. However, there might be at least two challenges remain for INN. The first challenge is that it might be hard for INN to capture the long dependency, right? Because the hidden state, especially the last hidden state, is the only memory module of the RNN structure. So it can be easy for RNN to remember what's going on recently, but it might forget what happened a long time ago. And so when we need to handle long documents, the problem becomes more severe. The second challenge is that it is very hard for INN to compute in parallel. The nature of INN is essentially a sequential model, so everything should be processed in a strict order. So when we want to process very long documents, the computation is very heavy and the time is very long. Then we might want to ask, can we have a new structure so that we can replace INN, but at the same time we still keep the property of INN? The answer is yes. But before we go to our techniques, we first take a look at what INN captures. So the first thing INN capture is the local context, as we mentioned before. And the other thing INN capture is the global interaction. Of course, as we mentioned, the global interaction INN can capture is quite weak. The third thing that INN can capture is the temporal information, which is essentially the ordering of the string. Okay. Now we will propose a new structure to replace INN, but at the same time we still keep the properties of INN. And it is also the key building block of our QANet. First off, we propose to use convolution to capture the local context. So as we mentioned before, the text is represented as a sequence of vectors. If we concatenate those vectors together, it becomes a matrix. And this essentially has the same form of representation as an image. Then we would like to borrow the idea from image to use convolution to capture the local context. So we can use different filters with different size to scan the context, the text, and then we can get a new representation. So those different sizes of filters are essentially the K-gram features in NLP domain. Okay. The nice thing about convolution is that it can be computed fully parallel. So the next thing we want to maintain is the global interaction. So of course, we can directly apply stack many layers of convolution, so to enlarge the receptive field of the convolution. But we may need log n layers to do that, where n is the length of the sequence. The other issue of this representation is that the interaction might become weaker as we step along higher and higher. So here we use self-attention to replace INN to capture the global interaction. So self-attention, as David introduced, is a special form of attention, which means that the only difference is that the key and the memory are the same. For example, here, this is a key and this is a query. They are essentially the same. So they just use the weighted average of itself to get a higher layer representation. And those weight is usually a normalized inner product between the vectors. Of course, we can also put some learnable parameter here to make it more flexible. But in our experiment, it does not help if we add more parameters here. Okay. So the nice thing about the self-attention is that it can be also computed in parallel, and it is all-to-all mapping. Okay. Yeah.
Just a second ago, you were talking about how, in the previous slide, you said you didn't have these extra parameters. So is that like on the words, before you do the dot products and take the softmax? So does that mean that you are discovering these key and value embeddings, or is that some that was talked about in the transformer, or is that did I misunderstand that?
I think my understanding is, so we could replace the dot product with a more complex distance function that has parameters, but in practice that doesn't work as well and is slower because if it's just dot product, it's just a matrix multiply. Yeah. Whereas if you have to put parameters in there, it blows up the memory.
But you're not doing the embedding in the key or another key.
So this is transformer in the UAS stuff.
Oh, okay.
This is just a high level explanation.
Just to clarify, there is a part that's being learned, which is how do you actually turn the word embedding into the three things, right? The query, the value, and the key, right? So that part is basically like a fully connected layer, which is being parameterized by data that are learnable, right?
In this case, the globe is a fixed pre-trained vector. It is not learnable.
I think he's talking about the first single transformer layer.
Oh,
so there is a memory key query projection.
Right.
Yeah.
And is that like a single fully connected layer, or is it multiple layers with nonlinear activations in between that has more?
It's a single that's split. There in multi-head attention, there are no nonlinearities.
Okay.
Yeah.
You probably could. I don't think it would help much, but.
Yeah. So for example, we can put a 3x3 matrix here, which is a learnable parameter, but it does not help in our case. Okay, so now let's take a look at the graphical structure of the different components. So the INN looks like a chain. Everything should be computed in strategic order, and convolution is like it's like a connected bipartite graph, but it's sparsely connected. But the self-attention is a densely connected bipartite graph. So we can see that the overall complexity, INN has the lowest overall complexity, but it needs to be computed in a strict order. So the sequential operation is ON. But for self-attention and convolution, we can compute in fully parallel. So the sequential operation is O1. Okay. So finally, we need to incorporate the temporal information of our sequence, which in RNN it is implicitly encoded. But here we just explicitly add the position embedding, just as introduced by David. It's a cosine function. So the nice thing of this position embedding is that it is still fully parallel. So now we come to our newly developed encoder. It essentially contains the position embedding, which is to encode the temporal information, and then a couple of layers of convolution, which is capture the local information, and also the self-attention, which is to capture the global interaction. And also we have a feed-forward layer, which is to project dimension. Of course, if you want to make it deeper, you need some other technique. For example, you need a residue connection, and you also need a layer normalization. Okay, this is called the one building block of the QANet encoder. And next, we will show that we can stack multiple of this encoder, so that we build the deepest.
You add the position embedding in every building block?
Exactly.
We did. I'm not sure it matters that much.
Okay.
Yeah.
I think it can be forgotten if you don't, but there's an identity connection from the beginning, so in theory it shouldn't matter.
Yeah. Okay, so conceptually, the difference between BiDAP and QANet is like we just replace the RNN with our QANet encoder, but it makes a significant difference. So the first difference is that QANet is by far the deepest neural network for NLP, which is about over 130 layers. The previous deepest one is about 30 layers. So because we can stack multiple layers of those encoders, but if you use RNN, usually you can only have 2 to 6 layers, and it does not help if you add more layers. The second thing about QANet is that it's the first QA system that without any recurrency. So because it's fully feed-forward, it can be computed very fast. For example, for training, the speed up is up to 13 times, and for inference, the speed up is up to 9 times. So of course, because this is a fully feed-forward network, we can borrow some techniques from the computer vision field to make it make the training more stable and fast, and also make it more generalized. For example, we apply the layer normalization, residue connection to make it train faster, and we also apply the L2 regularization, the stochastic depth, and squeeze and excitation with state-of-the-art in ImageNet classification context. So we apply all of this technique for free in our NLP. Yes.
Would you mind explaining stochastic depth and the squeeze and excitation trick?
Oh yeah, stochastic depth, like we have 130 layers. We can randomly discard one layer. This is called stochastic depth. Just like the.
So you truncate by like a layer 100 or something? Or
oh, not truncate. So in every step, we might sample. We sample whether we need to connect to the next layer. If not, we just skip. We totally discard that layer.
So every layer is f of x plus x. With some probability, you don't include the f of x.
Yeah.
It becomes identity.
Yeah. So the squeeze and excitation, just like we made the channel large, smaller and then make it larger. Then it proves to help in the last year's ImageNet classification task, right?
So you do that like 4 or 5 times throughout the entire step?
Yeah, something like that. Yep. Okay, so because QANet can be computed very fast, so we wonder whether we can put more data. But you know, for the squad data, they only contain 100,000 examples, so which is quite small. So here we propose a new data augmentation so that the system can generalize better. Data augmentation has been widely used in the field of computer vision and speech, right? So for example, for an image, you can do rotation, you can do reflection, you can add noise, or you can do whatever you want, maybe. Then so that you can have much larger dataset size, and then you can make your system generalize better. But this technique does not apply to NLP, because for each embedding, it's a discrete vector, and it does not make any sense to do any transformation or add noise to this vector. So here we propose a very intuitive idea to do those augmentation, just like which is called back translation. Thanks to the mature system, the neural machine translation system, we can get much better translation and more diverse translation. For example, if we put this sentence, primarily T has been used primarily for, previously T has been used primarily for Buddhist monks to stay away during meditation. And if we translate it to French and translate it back to English, then we get a new sentence, which is, in the past, the T was used mostly for the blah, 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 blah. Okay? So we show that this is, those paraphrasing is good for our system, and made our system generalize better. So actually, this technique is quite general, that it can applicable to a lot of NLP tasks that are not limited to QA. So for example, in our system.
Sorry, do you have a sense of how accurate that is? Because I saw a mistake in the French translation that was there.
It's not that very accurate. The good thing is that it's just like adding some regularization to the system. Yeah, just let it drop out.
If it is, earlier you were saying that, the other presenter was saying that the output that you're trying to predict is like a start and end position of the exact text you want to receive. So how can you know, like how that changes during translation? Good
questions. Yeah, we have some technique to do the post-processing so that we can still find the start and end point of the paraphrasing text. Yeah.
So like in this case, for example, like we might, for example, discard all translations that don't contain Buddhist monks, and then just essentially find what is the new position of Buddhist monk.
Oh, okay.
Yeah. So the answer is a string, but the label to the network is a start and end position into the context.
Okay.
Yeah. Okay, so the augmentation technique can help us get 1.1 F1 improvement, which is quite significant. And we use the English to French and English to German. Actually, it might also possible to use English to other language. So finally, David will introduce some transform learning technique to make our system better. Okay.
Alrighty. Cool. Thanks, Adams. So basically, I think that the attention and this bit on transfer learning is probably going to be the biggest things to take away today, because I think this transfer learning for text seems like it's about to get really big, and it's about to work shockingly well. So some of you may have seen this paper, Elmo. There have been a few variants at a high level. So earlier we were talking about like you can learn word vectors. And this is just going to say like, okay, the word bread maps to this vector. That you might want, let's see. I think a good example is like the word apple. Like apple farm versus apple stock, very, very different. But if all you have is an embedding for apple, it's hard to capture that. And so the key idea behind Elmo is to train a language model and use its internal representations as word vectors. So there's Elmo from LNLP, which uses I think they train a bidirectional LSTM to do language modeling. There's UlumFit from the FastAI folks, which is basically the same thing. Then there's one more from OpenAI, which is a forward language model with transformer and self-attention, all roughly the same idea. Going back, again, word vectors are kind of magical, but they're for a single vector. We want to be able to get meaningful embeddings that take into context everything that's around us. Kind of the old style way of training these was these sort of bag of words. So this is continuous bag of words. Now they can see it. So this is what word2vec was and skipgram. These techniques or something very similar was used to train the glove embeddings, which we were using. So now instead of sort of doing this in-painting task, we're going to go back to our language modeling world and just train, let's just say, one LSTM to go over and predict the next token. And in fact, we're also going to train one to go in the backwards direction as well, because it'd be nice if the embedding of when let's say I want to do something with a sentence, I feed it in. It'd be nice if the embedding here doesn't just include the information up to that point, but also includes information about the future. There are some tricks for making this not sort of a bidirectional thing, but let's see. But this works well enough. So if you train the language model to do this, called Elmo, this is a great slide from Sebastian Reuter. It improves all of the language. Just every NLP task gets better by a really, really big margin. So 81.1 to 85.8, that's really hard. You'll just have to believe me. So I think human performance on Squad is around 91.1. Squad is something being human on Squad also doesn't mean question answering is solved. Just as an aside, we still have a long way to go, but it's getting pretty good. And all that they're doing here is they take an existing model, instead of using word vectors, you run your bidirectional LSTM over it, and the embedding of a word is going to be a linear combination of the LSTM's internal state and the embeddings. And you can do a similar thing with the transformer. And so how we ended up using this in practice in our model is, so you have, in our case, the embedding of a word is going to be a function of A, look it up in glove vectors, B, character embeddings. So what that means is we have our token. What if it's horribly misspelled and isn't in glove? We still want to understand what it is. You just take the bytes and essentially run a small convnet over it to get the embedding. And so that helped us handle out-of-vocab words. And then there's Elmo, which is this bidirectional LSTM. And for our best model, we actually also have a machine translation system. This gets kind of crazy. I think in practice, you can probably replace all of this with just an even bigger language model. But in this case, we were using the exact Elmo model and pre-trained MT model that we had. So I suspect out of all of the NLP advances that this is going to be the biggest one, because it shows the largest data set people have trained these on is like 1 billion words, and the models aren't that large. And we can probably start training models that are 10 to 1,000 times bigger on 1,000 times more data, and it's probably going to get,
Well, something that seems a bit counterintuitive is that you already, let's say, some kind of transformer model.
Mm-hmm.
It already has self-attention.
Yep.
If you just, well, I guess you need something to optimize, but it seems like you could run that, try to train self-attention across the similar, massive corpus, and then worry about your application-specific loss for the rest, for the smaller data sets that you have.
Right. So that is, I think that's what.
Yeah, it's sort of like you would do a denoising autoencoder, just knock out words and try to predict them, I guess.
Yeah. So we can talk more about that. So that is basically that would be the idea of applying continuous bag of words, essentially. Like that's almost an analogous idea of like in painting. Like given the words in the context, can I fill in the word in the middle?
Well, except that your model would be the full,
Yeah.
position in tech. It would be. I mean, you would think the transformer would be a really good language model if it had a suitable loss to, predict missing words.
So you do some sort of in-painting loss,
Yeah.
So I think that's a powerful idea. I think language models seem to work well, but that has a nice benefit if you can look everywhere. Let's see. Where's it going with that? Yes, you have.
I mean, it's the LSTM, so it's looking almost everywhere.
I guess I don't have a good figure for this, but OpenAI I think is maybe the closest to what you're talking about. And they again do a transformer forward language model on a relatively large book corpus. One issue with training high quality language models is you have to have a high quality corpus. It's actually pretty hard to get good text that is over a few hundred words long. So he used the Alec Radford OpenAI used a corpus of children's book or like self-published fantasy books, I think. It's very strange. Apparently that's enough to learn something general about language. I'll leave that where it is. But it seems likely that as you get higher quality, like if you train it on all the books we have or you train it on, you can fine tune Wikipedia, for example, you'll get even better results. But in his case, for a lot of his tasks, in our case, we used like Elmo just as the embedding layer. And we freeze these weights. Like we don't backprop through them. It's more or less just extract the features, we'll train from there. You can probably replace the entire model, like you could train your transformer language model and then use that as the entire encoder. And so like in our case, where are we? Yeah, so instead of having additional encoder on top, this entire section could be like your language model and fine tune the weights. And then you'd have like a little bit on top. but most of the compute would be there. I think that would probably work very well. Let's see. So yeah, so I think at a high level, these ideas are great. They're only going to get bigger and bigger. I hope we can find an equivalent in images. Like these, yeah, I expect to just see all of the state-of-the-arts broken in every NLP data set over the next few months. Let's see. Yeah, so that's kind of the high level of what we had to talk about. So we walked through QANet as an example to kind of guide the stuff. We talked about attention, talked about transfer learning, some of these techniques for data augmentation. Unfortunately, we're not at the top anymore, and I checked this morning, it was updated again. But we're not, so I think we're now past human performance on Squad. There's a long way to go if you want to do question answering. We're still in the early days. Like I don't know how to, I don't know the narrative QA data set I mentioned earlier, for example, like these very long books. How do you process 50,000 words and do meaningful reasoning over it? There are a lot of very basic questions. But for the moment, thank you all for your time. I hope you learned something, and time for questions now. Cool. I think we've got a decent amount of time. Yeah.
So it's very, very impressive. I always like to ask, what are the cases that it gets wrong?
So I was trying to get, I wanted to get a live demo. I didn't, too busy sliding. I think the cases where you can definitely see it breaking is if there's multi-hop reasoning. Like if I had a pronoun that referred to someone and then that person is doing something further off, because it kind of requires multiple steps of binding. You probably have better intuition for the failure cases than I do.
And also some mismatch of. So for example, if the answer is the time, if there are multiple time in the context, it might point to some wrong time. Yeah.
Actually, I think that's so Squad v1, every question had an answer. Squad v2, which we didn't talk about, it's essentially sometimes the question won't have an answer. And that's because if I had an article about George Washington and I asked when did the Steelers win, it'd be oh, there's a year, they definitely won then. And so it's very it falls into these they want something with time, this has time in it, let me return that. But I think having these no answer cases helps with that some. But I think the biggest thing is still multi-hop. It's not going to do complex reasoning yet. Actually,
I was curious about that. Can you explain why? Because it does have depth, so in theory it can jump around the source text.
So I think one thing is Squad doesn't require complex reasoning largely because of the way the questions were generated, where it was here's a passage of text, look at it and ask me a question. People aren't going to do too complicated things.
And maybe because we do not add any mechanism to do reasoning in our framework. Basically, it's still pattern matching, I think.
Yeah, although it could in theory generate new patterns, couldn't it? Because they're just activations in the. I guess, sorry, maybe a related question is I've lost the picture. You have the query though.
Yeah.
Which? Do you know which one? Of the this sort of stuff. Oh, you want the actual? They're like this. Okay. Something like this.
No.
The next one, I think. The next one.
The next one, I think.
Yeah.
Does the query influence the attention over there?
The next one, I think.
Yeah.
Yeah.
Oh.
Yeah. So you have query to context, context to query. Yeah. So query should influence. Maybe not.
So I guess my feeling on this sort of complex reasoning stuff, I talked about this weight shared depth-wise transformer. I personally think that's a very powerful way to go. So in those terms, for example, they show if you have pure algorithmic tasks, add these two numbers together, or things that are very sort of mechanical require executing an algorithm, transformer can't really do that. But if you do weight sharing, it can. And so you seem to have entered a different class in terms of what you can represent. And I personally believe that having that sort of recurrence is important because there might be, let's say I have a 130 layer deep network, and sometimes there's some, you have to do this pronoun binding step or something. If you don't share weights, every layer has to somehow learn that separately through requirement, whereas you can imagine having a module that can sort of switch on and keep applying itself until it's done with its task.
How is, I guess, you were at the weight share transformer you were just talking about, how is that not just a recurrent neural network?
It's an RNN depthwise instead of lengthwise.
But, yeah, but also it's maybe a bit impoverished in internal state compared to typical recurrent networks. It's only got this sort of homogeneous view across the attention across the rest of the network, and it's only got little tiny heads. I mean, it doesn't save its own state more than some combination of the whole network.
I actually,
from a typical recurrent
so I
network,
argue
it's
that
state.
those networks are more, so instead of having a single vector as its state, now it has its entire tape. So instead of having a mechanism that operates on a tiny fixed size internal state, you have a mechanism that operates on memory. In this case, the memory is dependent on the size of like the document, for example. But like in a sense, the whole encoded structure is the memory that is operating on.
Yeah, but I know, but it just feels. I mean, it does look different from a typical recurrent network, which can focus on doing one thing across time. It's instead kind of every network every node sort of sees the same view of all of the data.
Yes.
And it has to work harder to remember to do one thing. Maybe. I mean, adding the single memory states in LSTM's made a huge difference to what they can do. They just remember to do the same thing. These don't currently have that in depth.
Yeah. It may be that if you do weight sharing, it may be able to do that. I'm not actually sure.
Well, it would help. That pushes you towards a basic RNN, but
Yeah.
not an LSTM. In the sense that you'd want the big, diagonal state memory.
You want the big, so I think it actually, let's see.
I think in two ways it's still some distance from an RNN.
Okay.
It doesn't have self-state based. It doesn't have any preference for self-state, even recurrent state. Sort of
I need to think, I'm not sure I entirely agree. I need to think more about it though. It's like because I think it can represent everything an RNN can once it has that recurrence.
That's not a good
but
thing
it's
to
not.
say. Well,
That's fair.
okay, that's a necessary but not. Again, going from, I would argue it's not really as powerful as an RNN just because it doesn't have self-state. It has to, attend to itself.
Okay, I want to think a little bit more about that.
But and it doesn't also have a forget state or a self state.
So,
Which
yeah.
remember the same thing.
Yes. So the attention can kind of, there are variants where you can.
You take the value
do it.
transformation out if you want to do that.
Take the value. Yes, makes sense. Any questions about anything we talked about?
So you briefly mentioned this image to caption network,
Yeah.
and you kind of showed an example of how to plug in the attention mechanism into the images, right?
Mhm.
So I'm not sure if you know the details of how that's done. Is that like pixel to word kind of correlation? Every single pixel or like a group of pixels?
So it's, let's say I have a 100 by 100 image. I apply a bunch of convolutions. I get a 10 by 10 by 128 feature map. I now have my LSTM hidden state. It's going to do a dot product with each of those, so 10 by 10 feature maps, so you have 100 vectors, and then do a weighted sum over those. So it's exactly the same, just instead of a sequence, instead of being like length 100, it's now 10 by 10.
I see. So it's not actually against every single pixel, but like a group of pixels that share.
Correct. It's against the encoded
I think
version.
basically the system just like replace this context as an image.
I see.
Yeah, and that's basically it.
It's like, yeah, exactly.
So the positional encoding that's like this crazy sum of sines and cosines is both, I guess, hard to understand, kind of unsatisfying, and it seems magical. Do you have an idea of like any other, I guess, more structural, or are there any efforts of like more structural or more like learnable ways of doing position encoding in this sort of transformer?
So the main other way is to actually have like a learned embedding for position 1, position 2, position 3, position 4. And it seems to work equivalently well. It doesn't seem to make any difference actually. You could also apply an RNN as the first layer, but that would get rid of your benefits of parallelism.
Sure, yeah.
Actually, there is a new submission to iClear this year. It's called Transformer XL. I think they use a new position embedding.
Oh, really?
Yeah.
Okay, I need to ask him about it.
You may take a look.
Okay, cool. Any other questions? Otherwise, I think we're out of time or near it.
you're good.
Anyways, we're good. Yeah.
It's still.
So you said there's 130 layers in the network, but from what I remember, there is one model encoding block on each input, and then sort of 4 encoding blocks after the clear context query intention, which I've been trying to do the math and
So there's a star next to those like that block is repeated n times and a different number of times in the encoder and decoder.
All right.
Yeah, and I would say the 130 layer part, like Squad is very much a regularization game. So it was like add more parameters, apply more dropout, add more augmented data. Like you can probably get equivalent performance with like distillation or something with like a much smaller model. But in our case, when we were sort of competing for that, the depth mattered.
Yeah, each of these such stack encoder contains 7 blocks of this Q&A encoder.
Something like that. Yeah. Yeah. Cool. Awesome. Thanks everyone for joining. Excellent. Some time. Yeah. I want to think more about this like R&D.